All right, so we begin our new chapter and our last chapter. It's about cryptographic protocols. It's a very fun chapter. You would get to learn about a lot of different problems and how we would solve them with crypto. Let's get to define what is a protocol to get the things clear. A multi-party algorithm or even a two-party algorithm has to be something that at least you have two parties that they need to work with each other in order to accomplish a task. So we would have some engagement that would make it very clear that why we need to have engagement, and one party alone cannot run the algorithm. You are depending on the some input or some computation from the other party. Um, so then, since it becomes multi-party, it means that we would have to have some interaction between the parties. Sometimes they want to do query, or they are connected with each other through a channel. And then, so we would assume that the channel is clear. Whoever is connected to this channel, they are they are able to send and receive messages. And whenever somebody send an undefined message or um, some, let's say, noise, or I would say, undefined messages, then the other parties are able to detect it on the channel and ignore it. So let's say right now we are working on TCP network, right? Most of the packets that we send and receive are TCP IP. And if somebody just start to make a new protocol and send some garbage message, since our network card adapter doesn't support that protocol, we would just ignore all those messages, right? So we have some standard ways to send and receive messages through UDP, TCP/IP, and some others, and those things are hard coded into our network card. If you start to send some random beats on the line or on the channel, then the likelihood that some network card adapter would pick that up and process it is very low, because it doesn't follow the formatting that the card is expecting. So that's why we say that the users are able to tell if some message is invalid. And then the goal of this whole thing is to accomplish a task. So the task could be very different um, depending on the nature and the problem we want to solve. So let's begin by giving you a very basic example that how that could work. So imagine we have three parties, A, B, and C, that they want to collaboratively share a random number or send some numbers and add them up together and then compute the sum so that they all utilize that as a random value. So I have a party A, I have a party B, and then I have also another party called C, and then every party would start to generate their own randomness. So the A would start to make the randomness of A, um, B would generate the randomness of B, and then C would also generate the randomness of C, right? And then the whole purpose is that these guys would start to send their values to everybody else. So A would send this value to B. So it says that, hey, this is my randomness through the channel. And then A would also send his randomness to C by saying, hey, this is my randomness. Let me change colors to make it even easier to understand. So C would send A saying that, hey, this is my randomness, and likely to the B saying that this is my randomness, and B would do the same thing as well. So R of B, and then R of B, right? So then if you are looking into the party C, the computation that he would carry out, he would turn around and say that, okay, so I get that the sum is randomness of A plus randomness of B plus randomness of C, right? So he compute the sum, and so everybody else will do the same thing. So you see that they collaboratively achieve one thing, right? So they have shared, everybody contributed to the sum somehow, and everybody now get to enjoy this, value that they share with each other, and they could start to do other things. Let's say that was the purpose of this small task. But a problem comes here when we are talking about crypto. Then Eve comes in the middle. Eve would come over here and says, you know what, I would, nobody can stop me to do whatever, so I would change that one to R prime of A, and also I have access to this channel, so I intercept this one, and I would replace that one with R prime of A, right? Since Eve show up and he did this computation, then if you look at the computation that C would get, for example, C wouldn't get R of A, he would get R prime of A, right? And also, if you look at the computation from B's perspective, so he get the sum equals to R prime A plus RB plus RC, and then A would compute, however, sum equals to, he doesn't send his R prime to itself, so he does add R plus RB plus RC. So you see that Eve, by this intention, made C and B to have the same sum, but A to have maybe some prime, because he added RA, which is different than R prime A that C and B received. And therefore you see that Eve can deviate this algorithm arbitrarily. He can basically block the messages, he can change the messages, or even he can read the messages, that is of course. But you see that when it was a very basic task that people just change values, and Eve just got in the middle and he was able to change these values. So even though we send these values RA in encrypted format, again Eve is able to replace that with some other random encryption, and he would be able to achieve his goal again, so that they intercept and interrupt this communication. So that is the thing about cryptographic protocols. So I hope that it becomes understandable now. So we just introduced our adversary, and then it's nice to discuss that again, what are the things he can do. We would, throughout this chapter, we would be focusing on two types of, basically we would categorize our adversary into two types. One of them is passive, that it means that we call him semi-honest. This sort of attacker can impersonate himself as one of the parties. He would, sometimes, he would follow the protocol honestly. That's what we say. He wouldn't mess up with the numbers. He wouldn't replace them. He would just do the description of the algorithm as you design, everything the same. But his goal is to, out of that, honestly, that he's following your protocol, with the interaction with the others, he tries to gain some information. It could be anything. We would have some concrete examples by the time that we get there, to make it a bit more clear in the context. But you can imagine that is a sort of adversary that is a nice looking adversary. He wouldn't deviate, he wouldn't delete the messages, he wouldn't modify the things. He would do exactly what your algorithm is saying. So the other one, that is active one, this one would act arbitrary. He would be somebody that we just saw on the previous page, that he would modify the messages, he would drop the messages, he would cause the protocol to abort, and he would misbehave in many different ways. Most of our effort over here is is to detect somebody like this that is deviating our algorithm or causing a harm into our computation, at least for the parties to understand that this message is not valid or something happened within the protocol, that they can detect it. And then depending on some design, there would be a way to recover from it or not. But the first promise is to make sure that we can detect that somebody is misbehaving in our computation. So that would be the first thing we want to do. So one of the first things that are actually a multi-party computation, and maybe you have never thought about it, is a key exchange and authentication, right? So the goal of key exchange and authentication algorithm is that two parties, they want to authenticate, Alice and Bob. Alice wants to make sure that she's talking to Bob. Bob wants to make sure that he's talking to Alice. And then at the outcome of this authentication, they want to share a key so that they can start to communicate. Maybe they want to share an AES key so that they can start to, send and receive some files. So when they share a key, I think throughout these protocols, you will normally see that we usually will talk about two different keys. We have two level keys. The first type of the key is what we call them master key, and these are some sort of keys that are lasting a little longer. So you can imagine that you have your public key cryptography. You generate a key. Most of the time you get a SSL certificate for it, and that key is valid for a year. Most of the SSL certificates are issued for a year. And that would be what we call it, your master key, your long-term key. Not long-term forever, but it is longer. And then we also have a notation that we call it from now on session key, that it is valid only for the duration of that, whatever communication you have. So here is a typical example and scenario when you will use it. When you connect, your browser will connect to, for example, gmail.com. Gmail.com has a long-term or a master key. The master key is embedded and is verified through a SSL certificate that your browser will download from gmail.com. We are able to verify that the validity of that SSL, and then Google, the Gmail, would tell his public key inside that certificate. So now you have the public key of the gmail.com, so you are able to utilize some way that saying that, okay, I know this is your key, so I want to maybe communicate with you, maybe I want to check my mails. So what you would do is that based on that, you would create a session key. A session key is a key that you would use it for the duration of that communication. Let's say you want to connect to the gmail.com for 5 minutes or whatever minute. You start to make a session key, you make that communication, and maybe you close your tab that is connected to the gmail.com, and that means that that session is over. Let's say an hour later, again, you want to check your mail. So you open a tab, you type gmail.com, and the whole thing would start again. You will verify the browser certificate and all those stuff, and then you will create a new session key that is different than the previous session. So every time that basically you have a tab, you connect to the server, you are generating a new session key. But the thing that doesn't change for at least a year, that the Google certificate is valid for it, that Google public key doesn't change. So that means that the first time you connect to the gmail.com, you verify the signature, you get the public key, you can store it locally, so that you know that you can use it for some time, at least a year. Then every time that you want to connect to gmail.com, you don't have to go through downloading the SSL certificate and all those stuff, right? You utilize the public key to generate the session key for that duration of the session. You write an email, you send it, and then you close the tab. Throughout all that communication, that session key would be the one that would encrypt or secure the communication between your browser to gmail.com. Once you close the tab, the session key would be deleted. You open a new tab, you generate a new session key. So this is like how most of the protocols would be used on the internet. So it is interesting, and it should be essential for you to know these terms like master key or session key. We are talking about the little longer lifetime key and the one that is quite short. So we have seen that we can do there are attacks around. So whenever they want to share a key, there would be eavesdropping. Somebody wants to, read the things that are sending and receiving on the line to see if they can understand or guess the key. There would be replay attack that essentially they would replay the same packets again. And if you didn't design this protocol properly, then you could leak some information or gain unauthorized access. There would be impersonation. For example, Eve says that I'm Alice, so there should be a way for us to tell that no, you are Eve. I know, based on some facts and information. And about the replay attacks, so it turns out to be a very serious issue. People would, take one packets that you have, Alice and Bob, let's say, have make some communication, and then suddenly, after that communication, somebody would record the packet and resend it again, and that would cause your algorithm or protocol to do something again. So let me give you an example. Suppose that you make a web service or make a server, and then you define that when you receive a packet, that your packet has the content of the packet has a specific number, let's say integer 20. Then with that, you will restart your server. Okay. So your network card adapter is reading every time that you receive a packet that it contains 20, then you will reboot your server. This would become a problem because when some attacker understand that is the case, even though he doesn't know the value was 20, he knows that by resending one packet, he doesn't even have to be the sender. He can just resend that and make it that it's coming from your IP address. Your server would restart, and that is all he wants to attack your system, that he would keep sending this packet, or we call it keep replaying this packet, so that it cause your server to keep restarting. So whatever service you're providing with that server, you can't do that because your server is keep restarting. So there are some workarounds to do that. People would add a timestamp to the packet. So your server would look at this clock and says that, well, I receive a message that it says I should restart myself, and it was sent like maybe 2 seconds ago. So you would define some time interval, and then if within this time interval it is okay, so you would restart. But if you receive this packet 20 minutes later, then your server wouldn't restart when you add the timestamp, because your server now knows that, well, the message, the timestamp is like for 20 minutes ago, but I have a tolerance of, let's say, 2 seconds. So this is beyond the timestamp or time interval that I should accept, and I would reject it. So maybe somebody would be able to reboot your system one more time with replaying the attack, and it would way past that 2 seconds. And then after that, he wouldn't be able to do that. So just because you add the extra information in the packet, and that is a timestamp. And sometimes you also resolve this by some nonce. We would use this one. You can imagine that it is some randomness, some random values that we send and receive between the communication. Let's say I ask you to, reboot the server, and then you send me the nonce to verify, or somehow with some, randomness that we can correlate our communication. That would be another way, and is widely used in servers to, to make sure that we can protect ourselves against replay attacks. So this is a very serious attack. I hope that with my example, you understand the context, and then we would see how, the we can protect against this so-called like replay attack. So the first system that hopefully we will get to finish it today is something that is called Kerberos. Kerberos is a system that it was designed in MIT many years ago, and then the goal was that there are a lot of students, there are a lot of employees on the campus, and then we also have a lot of servers on the campus. Let's say we have print server, we have email server, and then different servers that they provide different services. So the goal was that they wanted to achieve many things at the same time, but the one on the top is that they wanted to make sure that the workstation that the students or faculties are connected to, and the communication between that workstation to the server are secure. All of those communications, they remain secure. So they remain secure. The first thing first that they want to do is that you want to share a key from your workstation to the server so that you make sure that you can encrypt and decrypt the messages. So it is pre-public key cryptography, the time that they designed this one, and it uses the symmetric key cryptography. So we are only allowed to use AES, DES, and those kind of algorithms. We don't have something like Diffie-Hellman so that we are able to share a key directly. So it looked like that when we restrict ourselves to only use symmetric key cryptography, we need help from somebody to facilitate the communication or key exchange between the users. And the mechanism that they came up with is something called a trusted third party. A trusted third party, then in this protocol we know it as the authentication server, is a server that is trusted by everyone. So let's see, let's imagine in our campus scenario. So imagine in our campus we have NTHU.edu.tw. That server is, we say that everybody trusts that server. Why do you trust that server? Because, well, when you sign up at the school at just registry day, you receive an email address, your username and password is stored in that server, and then they would gather your information, such as your name, last name, and so on and so forth on the day of registry, and your address, your ID number, and all those stuff. And you join this organization and you kind of trust this organization with the way that they would hopefully properly handle your information and keep it secure. So that would be your entity that you trust and you're okay with sharing your information with. If we scale it up a little bit on the internet, like you are kind of trusting, for example, Gmail, that you create an account there and then you start to read and write your emails through their services. Well, the point is they have access to all your emails, right? So you trust gmail.com so that you create an account and you trust them that they don't share it with everybody else. No insider would read it and so on and so forth. That's how you will start to utilize their services. So that is the same idea, so that inside an organization, there is an entity that everybody can trust, and we call that in crypto trusted third party. So in order to set up the system, we have these entities. So we have this trusted third party that we call him T, and then we have a bunch of clients and then servers. So for clients, we call them A, like client A, that this client has a master key KA that has shared with the trusted third-party server. This is a master key. That means that this key would remain valid for a little longer, like let's say for a year or so, for maybe as long as you are in that organization. And servers would also share a master key, which is like an AES key. We call them key B, and with the trusted third party. And that key with the servers would also remain valid for a number of time. So now we are here to see how can the server help this A and B, which A is a client, B is a server, to start to communicate with each other. So I have the steps over here, but as usual, I will leave that one for you to read. Let's go into here and plan out an example. So we said that we start our organization. Our organization has some users, A1. Let me show users like this. So this user A1, we have user A2, and then user all the way to user AK, right? Or AN. Let's use AN so we don't have problem with the keys. Okay. And also we have some servers that we start to call them server B1, server B2, and so on and so forth. Let's say we have M servers in the network, right? So let's say the server B1, this guy is a printer server, print server. This guy is an email server, and so on and so forth. So, so these are the system that we have. These are the entities that we have in a campus. So I start to add as we go on. So what Kerber suggested that let's set up some server called authenticated server, right? So the point is this guy's A wants to communicate to B in a secure way, but we don't have a public key, and then we can achieve that. So this is the idea of the Kerberos. Let's define a server that we denoted here as T, or authenticated server. And then on the registration day, everybody would come here and configure, this guy would have a table saying that I know user A1, okay, and then imagine the user A1, a student A1, appear on the day of registration. They would randomly choose, he or she would randomly choose a key, K1, and then he would say, tell the registration office, or you would register yourself online and you choose your key, right, your password. And then you say, this T or registration office would keep this keys in a table, key of user 1. And let me draw this line. So these things are all behind the server, okay? All right. And then user 2 show up and then, says that I'm a student 2 and this is my key, long-term key that I share with you, and so on and so forth. And also at the same time, whenever they set up a server, somebody just set up a server B1 on the campus, so they assign a key for that server, key of server B1, and then this is going to be key of server B2, and this is going to be the key of server BM, and so on and so forth. So key of user 2, and so on and so forth. So they would also write them down so that they share a key B1 with key B1 and server B2, KB2, right? So they store all that information in a DB. And also they can also at the same time, so they can say that we would want to have an access list, so that B1 can be accessed by A1, A2, and so on and so forth. Maybe B2 can be only accessed by everyone too, right? And so on and so forth. But maybe B3 can only access by A10 and A20, right? So on and so forth. So they can define that access list, whatever that is, based on the function of the server and the type of the user, they can define that sort of list. So now here comes on the system. So by default, we said that there might be many servers on the campus, and then the user want to get a service, but before they start to receive a service, they need to find a way to establish a. Yeah, is there a question? Okay. So before they start to make a communication, so we know that everybody has shared a key with this trusted third party, and by default, they can start to communicate to this guy in a secure manner. And the idea is that they want to get this guy that to share a key, random key, so that they can start to communicate securely among themselves. So let's see how that works. The first package that we send is that this guy, A1, says that, hey, I am A1, I want to use B1, right? And this is my randomness, by the way, this is my randomness R of A, right? So let's see what does that mean. So A1 wants to, probably print something. So A1 says that, hey, trusted third party, I want to get a ticket to communicate with the print server in a secure manner. And well, the T would receive this information. He sees that A1 is a user and B1 is also a user. And he checked the access list and he says that A1 can access B1. And he's like, okay, it looked like that you are a valid user. I mean, of course, this is not the most secure way. We are talking about the simplified version of this protocol. And then if that is the case, then AS is going to return a ticket to this guy. A ticket is very interesting over here. So he would receive a ticket, and then the ticket is basically an encryption with the AES of key of A1, and then inside this ticket we have this information: a K, key K, RA, and then an L, B, encryption with key B1 of T. All right, where T equals to A, K, and L. Okay. So T says that, okay, if you are A and you send me this request and everything is valid, so he goes to this lookup table and he finds the key that he has shared, the T has shared with this user A1. And he says that I'm gonna encrypt some information and send it to you, the information called ticket, and is encrypted with the key that the A1 has shared. And if he is the right user that he is claimed to be, he should have the key A1 and he should decrypt these messages. Otherwise, the ticket that he received, if this is not a valid user, it's just somebody that is sending this information, he would receive a ticket, but he would never be able to decrypt and pick up these pieces of information. So let's see what are these pieces of information. The K is the random key that trusted third party draw randomly, generated randomly for A and B to use to communicate securely. So they're gonna use key K to encrypt and decrypt their messages among them. They don't have this key, so they are relying for this guy to make this key for them. But let's see how this guy could help them to share it. So if this A1 is the valid user, then he should know KA1, so he should decrypt this ticket, and then therefore he should obtain this K. He also received RA, so now he knows that this is the answer to his previous request, because RA was a random message, right? So he knows that he's getting this response through the message or request that he sent beforehand. L is some time interval that it says that this ticket is going to valid for an hour, for 2 hours. It's just some time. B says that, oh, actually it should be B1. That is saying that I know that this is a ticket for you to communicate with B1. And inside this one, he's providing some extra information that this user cannot recover because it is encrypted with the key of the server that he's supposed to communicate, which is encrypted with the key of B1. And so when this guy A1 decrypts all of these things, then he can go back and communicate to B1 saying that, hey, B1, this is A, right? And he sends the encryption of K B1 of T to this user, right? And of course, then B would be able to decrypt this message, and inside this decryption, it says that A1 was supposed to talk to you, and he checked that it is A1. And then the key that they are going to use from now on to encrypt or decrypt their messages is this K. So you see that this is the same one that the server is sharing between these two users. And then the L is the validity period for this communication to happen. So you see that with just like few communication with the trusted third party, the trusted third party is the person who would, generate this random key, and he would share this random key between these two users A and B to utilize this random key and start to secure their communication. I think we go up over here, so we follow with the text. So in the beginning, we saw that A says that I'm A, I want to talk to B, and this is my randomness, exactly the same message that we send over here. And then the trusted third party would respond to A by its ticket by sending this information that we've just discussed. Key is going to be the session key that they are going to use. And then then on the third message, we said that, A recovers the key, after he decrypted, check if it is not a replay message to prevent the replay attack. And then he would recover this ticket, E of encryption of T with key of user B. And then A now would send back another message to B that's saying that, hey, this is me. And then this is the ticket that I got from the or server, trusted third party. So I would like to communicate with you. And he also, you see that he started to encrypt something with the key, with the session key that he got, and already sending that to B. And that information, A or alpha, is just A, and T of A is just like some challenge right now. He's saying that when he received these messages and he decrypted it back, he should be able to decrypt it and send those back to me so that I can make sure that I'm authenticating the server B at the same time. So once B received this information, he can recover this information, and he knows that what is alpha. And then he check if this alpha is in a current time period of L. So that is how they authenticate themselves. And then B would start to send encrypt with the key K, the T of A, this only this piece that he received from A. And then that's how A can make sure that B is the one for sure that knows the key K, because he's the only one that could recover this alpha. And the challenge that he is encrypting that and send it back to me, and also this part, only this part, not the entire alpha. And so therefore he must be the one that he already has the key K. And then he recovered the key correctly. So now we can start to have our communication in a secure way with the key K, right? So communicate, right? So that is the entire purpose. So we wanted to A and B to share a key K so that they can start to communicate. Well, because we don't have a public key infrastructure, it was not possible for A and B to run something like Diffie-Hellman and achieve that key. So the way that we did that was that we introduced this server T over here. Well, it was a little bit tedious because we need to have a setup phase. When a student register or a server adds to the network, we have to, introduce it to our database. We have to update our access list, who can access that server. And then, with the idea of giving a ticket, and basically we would have our server T over here to share the key among the users. And that's how we achieve, the key sharing using this Kerberos system. The whole point was to not use the public key. But let's just quickly discuss that. What if we had the public key? We just discussed the case that we want to use the symmetric key, but nowadays that we have access to the public key, then you see that how easy it is. So in order to establish a session key without the master keys, so we use some publicly known parameters, P and G. We are talking about the group P, that these things are a part of the public knowledge, right? Everybody knows this P and G. It is installed in every browser, and these are the groups that mainly people are, servers and browsers are communicating with each other. So in order for Alice and Bob to communicate with each other, so we have some public information, P, G, and H. So we have Alice, we have Bob, and they want to share a key. What Alice would do is that Alice would generate A randomly from ZP, and then she would compute and send C equals to G to the A mod P to Bob. Bob would do the same thing. He would generate a B randomly from ZP, and then actually ZP minus 1. I should be very concrete over here. And then he would compute, he would send, let's say a D that is equals to G to the B mod P. And now both parties, that after they have exchanged this information, Alice receives G to the B, so D, and then she does D to the A, which is equals to G to the B to the power A, which is equals to G to the BA, right? Bob would receive C, and then he raises it to the power B, which is equals to C equals to G to the A to the power B, which you would get G to the AB, right? Of course, all the computations are in mod P. Then they would define the key to be hash of, this value, G to the AB. And Alice would also compute the same key K, which is the hash of G to the power BA. Remember that G to the BA equals to G to the AB, so it doesn't matter. So you see that with a very small effort, these two parties, even they've never seen each other before, they are able to share a key. And they didn't have to register themselves to any server. They didn't have to go through that tedious, communication with the Kerberos. I get my ticket, this is my nonce. With just like two-way of communication, they are able to share a key. And this is fantastic what we achieve with the public key cryptography. If you go back and you see that how many messages we send and receive, like 7 times. So we just reduce that. Actually 6 messages that we send and receive, so we just reduce that to only 2 messages, right? And then we already are there and we generate the key. All right, I think we can stop here. There is like some small examples, and we want to talk about the security of the things over here, and then I think this is a good moment to stop over here. So I just wanted you to see the comparison that without the public key cryptography, what was the tedious with the scheme that we have to go through with the Kerberos, and just with the public key, how easy and nice it is to generate a key. So every time that Alice and Bob meet each other, because they would generate Alice would generate a different A, Bob would generate a different B, so therefore they would always generate a different key. And this is the nice thing about the Diffie-Hellman scheme. All right. Let me see. Do we have any questions? No. All right. So this is it. It is the end of our lecture today, and next week we will continue with our public key cryptography. All right. Goodbye till next week, guys.